Hello, I'm Yang. Thank you for joining me for a series of videos that cover the basics and challenges in estimating a linear panel model with heterogeneous coefficients and variation in exposure. This series of videos is based on a paper of the same title, joined with Jesse Shapiro, and is prepared for Journal of Economic Perspective. Let me start with some motivation. Social scientists are often interested in evaluating the effects of a certain event, such as the adoption of a national policy. In this series of videos, we will use as our running example a study by Amy Finkelstein published in the QJE, which estimated the causal effect of introducing Medicare on healthcare expenditure. We're going to abstract away from many important details of her original analysis, but focus on the identification strategy of the causal effect. Causal inference in settings like this is difficult for the following two reasons. First, simply comparing outcomes before and after the occurrence of the event could conflate the effect of event itself with effect of some other policy changes around the same time. For example, Medicare was introduced in 1965 in the US to provide universal health insurance for retirees, and it was passed as a part of a Social Security amendment. But several amendments to the Social Security program passed in the early 1960s, so comparing healthcare expenditure right before and after the introduction of Medicare in 1965 could conflate the effect of Medicare itself. Another idea is to look at the outcome of a control group that was totally unaffected by the event, which can provide some benchmark for the counterfactual outcome. But in some cases, it's difficult to find such a pure control. Medicare was a national policy, so all 50 states in the US were affected. In such settings, it's common to take advantage of variation across geographic or other units in terms of the extent of their exposure to the event. And this approach to causal inference can be expressed in a heuristic model as follows. So in this linear panel model, the outcome is assumed to be composed of a unit effect, a time effect, a coefficient times an interaction between the observed event variable and the observed exposure variable, plus an error term that's assumed to be unrelated to the others. In this linear panel model, the unknown unit effect accounts for features of units that are time invariant. The unknown time effect accounts for background changes that may coincide with event, and the unknown error term accounts for other idiosyncratic factors. The term of the greatest interest is the interaction between the event variable and the exposure variable, as it captures the fact that different units are affected differently by the event. Then, as a result, the unknown coefficient in front of this interaction would capture the causal impact of events on the outcome. This heuristic model is, of course, simplified and does not include any covariates, but captures the essence of many models in empirical work. For example, the model of Finkelstein 2007 would imply an interaction between time indicators around the introduction of Medicare and a measure of access to private insurance prior to Medicare. I will explain why this is a good measure for exposure in the next video of the series. This heuristic model is usually estimated by ordinary least squares regression of the outcome on unit indicators, time indicators, and an interaction between the event and exposure variables. Because the model involves two sets of fixed effects, one for units and one for time, this OLS estimator for the coefficient is sometimes called the two-way fixed effects estimator. These two-way fixed effects estimator is widely used in the empirical literature. For example, Dubé and Vargas estimates the impact of income shocks on violence in Colombia. Their model would imply an interaction between the world oil price and a measure of a region's baseline oil production intensity. Stephanie and co-authors estimates the impact of a 1999 merger between two insurance companies on health insurance premiums. Their model includes an interaction between the post-merger indicator and the concentration index in different geographic markets prior to the merger. In the paper, we have more examples, and also in the online appendix of De Chansmatan and Dotfoy, you can also find more examples. Now, let me tell you the outline of this video series. The next video will discuss that in addition to the exposure variable, the policy or the event itself can have heterogeneous effect on the units. So the coefficient in the heuristic model can also differ by unit. We will illustrate this possibility using the Medicare example. We will see that in general, the two-way fixed effects estimator can perform very poorly when effects are heterogeneous, in the sense that it can fail to estimate the average of the unit's coefficients. In the third video of the series, we will see that in certain situations where there is no restriction on treatment effects heterogeneity and there is no group that's totally unaffected by the event, the identification of the average effect is so challenging that no estimator is guaranteed to estimate the average effect. In this sense, the issues we've identified with the two-way fixed effects estimator is not specific to two-way fixed effects estimator. It actually applies to any data-dependent estimator for the average effect. In the last video, we are going to discuss some solutions. A very active research area has focused on solutions when there is a group that's totally unaffected by the event. Building on work by De Chansmatan and Dotfoy 2018, we can replace the two-way fixed effects estimator with an average of a particular type of difference in differences type estimator and still provide a good estimate for the average effect even when there is treatment effects heterogeneity. The goal of our paper is to translate the prior econometric work on two-way fixed effects estimator, and hopefully by the end of this video series, you'll be able to understand the identification challenge when we allow for unmodeled treatment effects heterogeneity and learn about potential solutions.